So unit 3, we're going to begin with working again with polynomial functions. This is going to be chapter 5, section 1. So again, we're going to be working again with functions. So just remind you what a function is. A function exists when input values, which now we know that word is the domain. Remember, input values are those x values typically. They're going to go through a series of calculations and they're going to result in output values, which a lot of times we use the word range for that. Again, remember, output values are those y values. Remember, there's basically 3 views of a function that we're dealing with. We're working with an equation. A lot of times you'll see that f of x notation, f of x equals, and then you'll have some type of function, either if it's linear or quadratic or cubic, so forth and so on. We also have what's called the table. So that's that big T where you have your x values and your y values. And then you have what's referred to as the graph. So you have your x-axis and your y-axis, and you'll have the graph of the function on the graph. So we've been working with those 3 views, and we're going to continue to do so in this chapter as well, in this unit. Some things to be familiar with, though, as we move forward. It is important to pay attention to that what a negative exponent means, and also what a rational exponent means. So let's start with the negative exponent. If I have 3 to the negative 1, 3 to the negative 1, the negative 1 means to take the reciprocal of the 3. So if I have 3 to the negative 1, that negative 1 means to turn that into a fraction. In other words, it turns into 1/3. So it kind of means to take the reciprocal, which means to flip it upside down. Remember, a 3 is 3 over 1. It is a rational number. And when you flip it, it just becomes 1 over 3. 2 to the negative 3rd, the negative 3 means to take the reciprocal of the 2 and then actually cube it. That means, raising it to the 3rd power. So we want to cube it. So 2 to the negative 3rd means to take the reciprocal of the 2 to start with. So it becomes a 1 over 2. But then you still got to cube it. So that becomes then 1/8. So similarly, the following can be expressed using negative exponents. So if we have a fraction like 1 over 3rd, we can actually rewrite that using a negative exponent, 3 to the negative 1. Those are equivalent. They mean the same thing. If I have 1/8, notice how I can write this as 8 to the negative 1. But then 8 is the same thing as 2 cubed raised to the negative 1. And when you have a power to a power, we actually multiply those 2 exponents. And that becomes then 2 to the negative 3rd. So those are equivalent. So 1/8 can actually be expressed using a negative exponent. Now, working with rational exponents, rational kind of means there's a numerator and a denominator, typically. But again, whole numbers are rational as well. But we're going to be talking about what we refer to as these fractional exponents, if you will. So rational exponents can mean to take the root of the number. That's when we start to use this radical symbol. So let me go and put that over there a little bit closer to the, we'll put that a little bit closer. So that's the radical symbol. And radical symbol, we have, this is the square root symbol. This is the cube root symbol. This would be like the 4th root symbol. But this little check mark thing, this actually is called the radical symbol. So this is the radical symbol with the 3, which stands for cube root. If I have the radical symbol with the 4 there, that actually stands for 4th root. So 9 to the 1/2 actually stands for the square root of 9. And the square root of 9 means what number squared gives me 9, and that would actually be a 3. If I have 125 to the 1/3, this is described as the cube root. So the cube root would be then this radical symbol with a 3. So the cube root of 125, and that would be what can you raise to the third power that gives you 125, and that would be 5. 16 to the 4th would actually be 4th root. So that's going to be the radical symbol with the little 4 here. And if you put a 16 aside there, that's now the 4th root of 16. And what can you raise to the 4th power and get a 16? That would be a 2. So similarly, if we see these expressions here, I can express these using rational exponents. So the square root of 25, we can also write as 5 to the 1/2 power. Notice how the denominator is a 2, that stands for square root. If I have the cube root of 8, that's the same thing as 8 to the 1/3 power. Now I'm using what's called a rational exponent. The 4th root of 625 can be expressed as 625 to the 1/4 power. So we have that going on. So those are some things we may want to be familiar with as we move forward. So what is a polynomial function? So again, it's hard to explain that in words, so we just use this notation. F of x equals, and you have this a to the n times x to the n plus a to the n minus 1 times x to the n minus 1. That minus 1 looks a little high there. So let's kind of get that a little bit lower. So that should be actually a to the n minus 1 and a little bit lower. So that n minus 1 actually determines that this is like the next term in the list. And also, one of the things to pick up on is the exponents in n minus 1. The exponents go in decreasing order until you get down to what's called the linear term, a to the 1 x, that's the linear term, and then plus a to the 0, that's going to be referred to as the constant. So again, these a's, a n minus 1s, a to the first, a sub 1, I should say, and a sub 0, these are all going to be real number coefficients. A sub n is actually going to be considered what we refer to as the leading coefficient. He's out in front. So the leading coefficient is the one that's associated with the highest degree term. Since n is going to represent the highest degree term, the a sub n is actually considered the leading coefficient, the number in front. A sub 0 is going to be the constant. That's just going to be some number without the variable. Because remember, when you're dealing with the constant, the exponent of x to 0 is actually a 1. So the variable drops out on the end. So remember, the degree of the constant is actually a 0. The other thing we have to pick up on is the exponent of n is a whole number. And then also n defines, it's going to define the degree of the polynomial. So the highest degree of the polynomial is going to be also the degree of the polynomial. So that's what we're going to be looking into, is this type of notation here. So when writing a polynomial function, the highest degree defines the degree of the polynomial, and the highest degree term is also called the leading term. He's the term out in front. So altogether, he's described as the leading term. So some examples of some polynomial functions. So if I have f of x equals 5, that's an example of a polynomial function. G of x equals -3/4 x plus 2, that's going to be a polynomial function. And we should recognize that this is a linear one, which means this -3/4 is a slope, and this 2 is a y-intercept, and we could graph it accordingly. H of x equals x squared minus 4x minus 5. Notice how that would be quadratic. This one looks a little different. F of x equals x minus 2 times the quantity x plus 3. That's actually going to be a polynomial as well. Notice that if you multiply the x's together, the x times the x, that's going to actually give you this x squared. And that's going to tell you that the degree of this polynomial function is actually x squared, because All you gotta do is multiply the x's together to get your degree there. K of x here, notice I have negative x cubed plus 2x plus 7. So that would also be an example of a polynomial. Notice it's missing a term though. Negative x to the third, you actually have 0x squared is missing, plus this 2x plus this 7. So the degrees go, remember they have to count down. So degree 3, degree 2, degree 1, degree 0. So when there's a term missing, it's understood that its coefficient is actually 0. So that's why that term is missing, because when you multiply by 0, that term just drops out of the problem. So some examples of some functions that are not polynomial functions. As we said earlier, to be a polynomial function, the exponent has to be a whole number. So when we're talking about polynomial functions, the exponent has to be a whole number. So if you notice here, f of x equals the square root of x, that's actually x to the 1/2. So its exponent is not a whole number. So that's why it's not a polynomial. H of x equals 1 over x cubed. Notice how again we have this x to the negative 3 here. So that's the same thing, which means the exponent of the variable is a negative number. And again, to be a polynomial function, the exponent cannot be negative. Similarly, you cannot have a fraction where the variable is in the top and the bottom. That also creates something that is not a polynomial function. So again, identifying key vocabulary of a polynomial function. So one of the first things to pick up on is a polynomial function must be written in what we call standard form. Standard form means the largest exponent to the smallest exponent. So if I'm going to look at this example here, notice that it should be actually negative x to the third plus 2x squared minus 4x plus 6. That would be the correct way of writing it. So if the terms are out of order, it's up to us to put those terms in the correct order. The degree of the polynomial is the largest exponent. So the degree of this polynomial comes from the leading term, which would actually be the 3. So this 3 would be considered the degree of the polynomial. If I want to identify the leading coefficient is this a sub n. That is going to be the number in front of the variable. So remember, x to the third is the variable part. The number in front is actually, there's a negative there, but it's understood to be actually a -1. So the leading coefficient is actually going to be a -1. The constant a sub 0 is going to be the last term, but again, it has to be a number. It can't be something with a variable, because the constant has to have a degree of 0. So in this case, 6 would be considered the constant. So remember, the degree of the constant is this 0. So keep that in mind. X to 0 is 1. We don't show that in the problem. So notice how you have this 6x to the 0. That really means 6 times 1, which is 6, and that's why its degree is considered 0. So if I look at this polynomial function here, I have g of x equals x minus 3 times x plus 4 squared. If I want to rewrite in standard form, they want me to actually multiply this all out. So if I look at this, we have to evaluate exponents first. So the x plus 4 squared has to be done first. So remember, if this is a perfect square, this actually creates a trinomial. And the shortcut is all you got to do is square the first term. X times x is x squared. To get the middle term, all you got to do is multiply the x times the 4 and then multiply that by 2. So x times 4 is 4x. If you multiply that by 2, that's going to give you this 8x. And then if you square the last term, 4 squared would be 16. So it's going to be a plus 16 there. And then you would have this x minus 3 times that. So that's how that would expand out. But notice I really don't have enough room there, so I need to really bring this over a little bit. X minus 3 times x plus x squared plus 8x plus 16. So if I want to expand this out, I have to kind of distribute the x through there. So this x has to go through each one of these terms to start with. So I have x times x squared would be x to the third. X times 8x would be 8x squared. X times 16 would be 16x. Once you do that, we then have to bring the -3 through. So it's got to be a -3 here, this -3 to there, and this -3 over to there. So I have to do that distributive property with that -3 as well. So -3 times x squared is -3x squared, and I'm going to put this underneath to line up my like terms. -3 times 8x is going to be -24x, line up my like terms. -3 times 16 would be -48. So I would have then x to the third plus 5x squared minus 8x minus 48. So to write it in standard form, I would have to just multiply that all out. X to the third plus 5x squared minus 8x minus 48. So what's the degree of the polynomial? The degree of the polynomial is going to be the highest degree term, which is going to be this 3. If I want to identify the leading term, that's the front term. That's going to be this x to the third. If I want to identify the leading coefficient, it's the number in front. Remember, that's the a sub n. That's going to be this 1. If I want to identify the constant, that's that a sub 0. That's the last guy. That's going to be this -48. He's going to be the constant. So that's going to be some key things to pick up on is leading term, leading coefficient, and constant. And we've used those words before. So if I look at these polynomial functions here, this first one is called the 0 function, and its degree would be 0. So it's going to be the 0 function. And the graph, if I look at it, it's actually going to be the x-axis. So if I graph this, this means again y equals 0. Y is equal to 0 is the x-axis. So the 0 function really represents a graph along the x-axis. So f of x equals 8 sub 0. Notice how that's going to also have a degree of 0. That's the constant. Again, he's going to be considered the constant function. And the graph of a constant function is also going to be some horizontal line. So its graph is going to be whatever a sub 0 is. So a sub 0 is going to describe where you are with that. So the y values have to stay the same. So it stays horizontal. So if I have f of x equals a sub 1 times x plus a sub 0, that's going to be a degree 1 polynomial. And it's called a linear function. Linear functions are going to take the form of a line. So from a graphing perspective, it's going to take on some type of slope, and it's going to run either that way, or remember, it depends on whether the slope is positive or negative, in which way it's going to run. F of x equals a sub 2 x squared plus a sub 1 x plus a sub 0. That's going to be a degree 2, and again, we call him a quadratic function. So that is a quadratic function. So again, a quadratic, if you recall, if I'm graphing it, it's going to be some type of what we call a U-shaped graph. So it's going to take on the shape of a parabola. But remember, that parabola can't open up or down. depending on what the leading coefficient is of the x squared. So the graph of a polynomial function will be described as smooth and continuous. So I don't know if I can do that very well here, but the graph of a polynomial function basically is going to be a nice little smooth graph that kind of turns every once in a while. It's going to be smooth and continuous. So it's going to take on a look of something like that. It's going to have the smoothness, and a lot of the polynomial functions we're going to deal with, since they're going to be above degree 2, they're going to have more than one term in them. So the first thing we'll get into is it's called the power function. If a polynomial function has only one term where the exponent is greater than 0, this is going to be called the power function. So if this would be an example where the degree is 1, so it's going to be an example of a line. This is going to be an example of a 2, so it's going to be an example of a parabola. And notice how we have a 3. We haven't really talked about these yet. So this is going to be new to us. And this one here, where the degree is 4, that's going to be new to us. So what we're going to try to do is develop strategies to graph polynomial functions that are degrees 3 and higher, because we're kind of familiar with lines and quadratics at this point. Now we're going to try to get a little bit more familiar with cubes and 4th degree functions. So remember, graphing strategies such as stretches and compressions would be involved still. So keep that in mind. This multiplication of 2 is going to kind of make the graph vertically stretched. So notice how the graph gets steeper. It gets pulled further away from the x-axis. Where I have this negative 3x squared, notice how this negative 3, it's going to do two things. The negative is going to make it open down, and the 3 is going to, again, vertically stretch it. So again, it should be narrower because those values should move further away from the x-axis, which makes it a narrower one. This 4, again, is going to become a vertical stretch, but we have to kind of remember that a cubic function was that snake. So this is going to be a snake that's going to be even steeper. And we really haven't talked about this x to the 4th guy. We'll talk about him as we move forward. But also how the negative 1/2, the negative would make a reflection. The 1/2 would be a compression. So it has two things going on there, a reflection and a compression. So properties of power functions that are even. So even kind of means the exponent is an even number. So if the exponent is an even number, even functions are going to be symmetric to the y-axis. They're also going to be U-shaped. They're going to take on that U shape. The domain values is going to again be the set of real numbers. So remember, as an interval, that's going to be from negative infinity to infinity. That means every number works in the domain. There's not any values I cannot put in for x and get a corresponding y value, because remember the definition of a function is for every input value, there has to exist an output value. So every number that we can think of, if it's put into these functions, it's going to have a corresponding output value or y value. The range is going to be greater than or equal to 0. So in other words, its vertex is going to be at the origin. And also, what I say about the power function, there's not actually a coefficient here in this one. So we're taking out the any kind of reflections and stretches at this point, or compressions. So keep that in mind. It's always going to start out with a vertex concept at the origin, and it's going to be opening up. So it's going to take on this look to start with. So some key points that we'll be plotting: negative 1, 1, 0, 0, and 1, 1. They're going to exist on all these graphs that look like this. Also, we pick up on this: as the exponent n increases, the graph is going to become much steeper where x is greater than 1, or where x is less than negative 1. So the graph is going to shoot up much more sharply vertically. What's really interesting is where x is close to the origin, the graph is going to be much fatter. It's going to lie closer to the x-axis. So we're going to talk about that a little bit. So being really close to the origin, it's going to get a lot flatter in that situation. The end behavior, and then again, we're using some fancy notation here, but what this reads is as x, and again, this arrow kind of means approaches, as x approaches negative infinity, as x gets further and further to the left, what's happening is the y values will be approaching infinity. So this kind of means as x approaches negative infinity, the more you go left, the y values should be going up even more. As x's approach infinity, so if we go to the right, what's going to happen is the y values are also going to be approaching infinity. They're also going to be opening up. So if I want to use the graphing utility, I can graph a few of these functions. See if I can make that happen here. We'll probably keep that the same size. We need a graphing utility. So if I have y equals, if I graph this x squared, so hit the x there and then the square button. If I hit the graph button, looks like my window is not set right. So if I hit the window, if I go, I can kind of see my window settings are all over the place. So if I go back to zoom, number 6 will get me back to my normal window. And so there's my parabola there. Notice there is this point 0, 0's there, this negative 1, 1's there, and this 1, 1 is present. So those 3 points are present. So if I graph that over here, that 0, 0, oops. So that, I'll graph that in blue as well. Let's see here. So 0, 0 is present, negative 1, 1's present, and 1, 1's present. And the graph takes on this little smooth U-shaped parabola. So that's going to be the x squared function. Okay. So that's going to be the f of x equals this x squared. F of x equals x to the 4th. Let's see what this color is over here. So if I go down to y2 and graph that one as well, x to the power of 4. Let's just see how it looks if I graph it. Notice how again, it's going to be in red. So if I have a red color over here. Notice how again, you still have this 0, 0, this negative 1, 1, and this 1, 1. But notice how the graph is much steeper. Okay. And notice how it is fatter. It's more flattened as it goes close to the origin. So it's a lot fatter there, flatter, if you will, either way, around the origin. So if I graph then, and I did that one in red, f of x equals this x to the 4th. And notice how hard it is to, I'm just not real good with my pen here, but let's see, y equals this x to the 8th. If I graph that one as well, in graph number 3, x to the 8th power, if I graph, notice that one's in black, and notice how it's even steeper, and it's even flatter than the x to the 4th graph when it comes close to the origin. So it goes up much more sharper, and it's much fatter at the origin. So notice how it's actually inside the x to the 4th graph. As it comes down, it's even fatter around the origin, and it is much steeper still as we go up the other direction there. And so it would be this x, f of x equals this x to the 8th graph. So they'd have that going on there. So when the degree is even, there's just this one term, x to the 4th, or this one term x squared where there's even exponents. The graph is going to take on this U shape. But again, as the exponent gets bigger, the graph gets much steeper and it gets much flatter at the near the origin. So the other thing we got going on is what's called the odd power functions. Odd power functions, the exponent is now going to be an odd number. So like 1, 3, so forth and so on like that. Odd functions are going to be symmetric to the origin. And remember, that's going to be, especially when we talk about 3, 3, 5, and so forth, those are going to be snake-like. Remember, degree 1 is a line, but degree 3 will be more snaky. Notice that the domain and range here on odd degree functions, the domain and range is a set of all real numbers. But notice how a U-shape actually had a boundary. These will not have boundaries on the domain or the range. They're going to be the set of all real numbers. In other words, they're going to go from negative infinity to infinity. The graph is always going to contain the points -1, -1, 0, 0, and 1, 1. Notice that -1, -1 is actually in that third quadrant. Okay. As the exponent n increases, the graph again is going to get steeper when you're left of -1 and to the right of 1. And again, as the graph gets nearer to the origin, the graph again is going to flatten out as it gets closer to the x-axis in the origin. So as it's going to flatten out and get closer to the x-axis, I should say. So as it gets nearer to the origin, it's going to flatten out, which means it's going to get closer to the x-axis. As far as end behavior goes, what's happening out to the far left and to the far right, as x approaches negative infinity, in other words, as x goes further and further to the left, the y values are also going to be approaching negative infinity. So from a graphing perspective, what that means is this end behavior is going to kind of go down like this and up like this. That's going to be the end behavior for that, because on this next one, notice how it says x approaches infinity, y is going to be approaching infinity. So as you go to the right, the y's are going to be going up. So as you go left, the graph should be going down, left and down. As you go to the right, the graph should be going up. And somewhere here in the middle, it's going to have this characteristic of a snake. So we'll see more of that as we move forward. So if I want to graph the polynomial function using transformations, notice how this has a 1 minus x to the fifth. And notice how usually we like to write this as negative x to the fifth minus or plus 1. Notice this graph should have a vertical shift of 1, and it should have a reflection. So it's also not a bad idea if I want to use the calculator to get a couple of ordered pairs to make a sketch of it. Let's see if I can make that happen. So let's go here to y equals, and let's just go ahead and just clear these all off. I don't think we need them anymore. So if I type in 1 minus x to the fifth, or negative x to the fifth plus 1, so negative x to the fifth plus 1. If I hit the graph button, notice how the graph did shift up, and notice how the graph also, that negative made it reflect. So remember that the original function would have done, this here. Oops. My original function would have kind of done this, kind of snaked down this way. But that plus 1 made the graph go up 1 to here. And the negative kind of means the graph reflects over the y-axis. So the part that was going up is now going to be reflecting down, and the part that was reflecting down is now going to be reflecting up. So it kind of gets mirrored across the x-axis there because of that negative. Now, if I want to get a little bit more special with it, if I hit the second button and hit the table button, I should be able to get some ordered pairs here, but let me see what my window's doing here. My window is okay. Let me change my table set. Hit second table set. Notice how my independent variable is on ask. I need that to be automatic. So now the graphing calculator will do all of it for us, but ask means I choose the values to go in on that. And that was under table setup. So if I go back to second table, notice how it does give me this 0, 1. If we go, so we can go up here a little bit. So we have this -1, 2 would have been a point we could have located. So -1, oops. So -1, -2. We had this 0, 1 we've already got, and this 1, 0 would have been maybe here. You kind of see that this graph now kind of takes on that look there. Notice how those other points are really hard to plot because it grows in a hurry. So we really don't get to plot a whole lot of those points. All we really just are trying to do is identify some of the behavior that's going on in the graph. So if I look at this function here, this next one, y equals 1/2 x minus 1 to the 4th. Notice how we have this x to the 4th. This x to the 4th means it's going to kind of take on this U shape. Notice that this 1 on the inside is going to make it shift to the right one. Because remember, your transformations inside is going to be opposite what you see. That's going to be a transformation to the right one. And this 1/2 should make the graph get closer and closer to the x-axis. So if I remember those critical points there that we talked about, I think they said -1, 1 existed, 0, 0 existed, and 1, 1 existed. What should happen is the -1 should make my x values move to the right one. So that should turn that into a 0. That should turn that into a 1, and that turns that into a 2. The 1/2 would compress my y values because you have to multiply the y values by 1/2. So that turns into a 1/2. 0 times 1/2 is still 0, and 1 times 1/2 would be 1/2. So if I plot those 3 points, you have, if this is 1 here, 0, 1/2 would be located here. 1, 0 would be located here, and 2, 1/2 would be located here. And remember, the U-shaped graph kind of takes on this U shape, and notice how it gets a little bit fatter when you get close to that middle point now, because it was going to be the origin, but now it's going to be in between here since that point's been shifted over to the right one. So it's not going to be getting fatter where, remember, the point 0, 0 is now going to be at 1, 0. So if I type in this graph here, we have y equals, if I clear that off and type in, again, I can put that in parentheses, 1 divided by 2 for 1/2. And then in parentheses, I have x minus 1. And that's raised to the 4th power. If I hit the graph button, I should get kind of what I sketched over there, just a much smoother graph. Okay, so your graphing calculator can also kind of help you verify your transformations and stuff. So that -1, since it's on the inside, is going to make it move right one. And that 1/2 is just going to make it get closer to the, that's called a vertical compression, closer to the x-axis. So this is where this takes us. So finding the zeros of a polynomial function and their multiplicities. So getting back into some algebra skills. So the definition of a zero has some other meanings. A zero is what makes the function turn into 0. So f of x equals 0. In other words, y is equal to 0. Okay, so keep that in mind. So we're going to let r represent a 0. So f of r, if that gives me 0, then we have what's called a 0. R will be some type of real number, but what it's going to do, it's going to actually make the output value 0. So we're looking for the input value that makes the output value 0. So in other words, we're looking for the value of x that makes y turn into a 0. So what's going to happen is r will also be an x-intercept, because you remember on a graph, an x-intercept, that's when y does equal 0. So if r represents the 0, then x minus r is actually going to represent the factor of f. So we'll see how that comes into play. So to find r, it's going to be the real solution to the equation f of x equals 0. So remember, this is where our factoring skills will have to come into play. So another thing we're talking about is the definition of multiplicity. Multiplicity is the number of times the factor x minus r repeats. So it also is how many times the 0 repeats. In other words, how many times r repeats. What's going to be cool is the multiplicity will describe the behavior of the graph at the x-intercepts. In other words, at these zeros. So again, when we talk about graphing though, those zeros, we use the word x-intercepts. So let's see if we can put this to work here a little bit. So find the polynomial function who has the following zeros. So we're telling you that the degree is 3, and these are the zeros, -4, 1, and 3. So remember, r represents the 0. X minus r is going to represent the factor. So let's see where this takes us. So the degree will help us with the multiplicity. Since there are 3 zeros, the degree will remain 3. So that means each 0 has to only repeat 1 time. In other words, the multiplicity is 1. So each one of these factors is only going to repeat 1 time. As I said, we're going to use x minus r to create the factors of the polynomial. So since r was -4, 1, and 3, we're going to have then x minus say -4 times x minus 1 times x minus 3. And again, since writing a function, we have to use this f of x equals this. But notice how x minus -4 really just means x plus 4. So that sign basically just changes x minus 1 times x minus 3. So when you turn these into factors, just notice that you're just going to have this x, and then these signs are going to change. Since that's -4, it turns into a +4. If it's a +1, it turns into a -1. If it's a +3, it turns into a -3 when we go back, reverting it back to factors. Since no other information was given, we're going to just assume a was equal to 1. Okay. So we're going to put a 1 in front, but again, if you put a 1 in front, nothing happens to it. You may be required to expand these out. So sometimes you can get away with leaving it in this form. I usually do x plus 4 times x minus 1 times x minus 3. That would be what I would call the function. But if you have to expand it out, we have to multiply this all out. So x plus 4 times x minus 1 would be x squared, because x times x is x squared. X times -1 is going to be -1x. Then you multiply 4 times x would be positive 4x, and 4 times -1 would be -4. So that's going to turn into this x squared plus this 3x minus 4. But we still got to multiply that times x minus 3. So we still got to multiply this x squared plus 3x minus 4 times this x minus 3. So again, I'm going to just take the x through. X times x squared is x to the 3rd. X times 3x is 3x squared. X times -4 is -4x. Then I got to bring the -3 through. I missed a term here. So x times x squared was x cubed. X times 3x is actually 3x squared. X times -4x is -4x. That looks good now. -3 times x squared is going to be -3x squared. -3 times 3x is going to be -9x. And -3 times -4 is going to be this plus 12. So if we put that all together, I should have then x to the 3rd minus well, the x squareds cancel out, so minus 13x plus this 12. So my function actually is going to be, if I expand it all out, f of x equals this x to the third minus this 13x plus this 12. So it's not a bad idea to practice that. You can try putting it in not expanded and see if it takes it, but keep in mind you may have to actually expand some of those too. So a few more examples. Let's find a polynomial function whose zeros are -1, 3, -4, and 0, and its degree is 4. So to do that, I'm going to have this f of x equals this. Let's have a -1, so it's going to be x plus 1. The signs go backwards. So I'm going to write the factors here again. So those are the zeros, and I can change the zeros into factors. So that 3 is going to make that an x minus 3. And that -4 means you have a x plus 4. And x minus 0 would just be x. It would look like that. And notice that since the degree is 4, we just have these, all the multiplicities are just going to be 1. So I don't have to put any exponents here. All these are just going to have an exponent of 1. If I expand this all out, I have x times x is x squared. So if you do your first, you get x squared. If you do your outer, you get a -3x. Your inner would give you a 1x. So it's going to be a -2x. And then your last would be a -3. And then I can multiply x times x plus 4. So it's going to be x squared plus 4x. Then I got to multiply that all out. So I have to multiply the x through there. X to the 4th minus 2x to the 3rd minus 3x squared. Then I have to bring the 4x through. So it's going to be positive 4x squared. I'm sorry, 4x to the 3rd. And then minus 8x squared. And minus 12x. So if I put that all together, f of x is going to equal then x to the 4th plus 2x to the 3rd minus 11x squared minus 12x would be the expanded form of that. On this next example, they give us these 4 zeros, but also they give me this extra piece of information. They say the y-intercept is 16. So remember, that is an ordered pair, 0, 16. Remember, a y-intercept, the x value is 0. So this is actually going to allow, the y-intercept is actually going to be used to find the value of a this time. So before, the a was just going to stay at 1. Now we actually have to find the value of a because they gave me some more information. So if I have this f of x equals this, so my zeros are all, there's just 3 of them, so the multiplicity is just going to be 1 for each one. So that 4 means I'm going to have an x minus 4. The 1 means I'm going to have an x minus 1. And this -5 means I actually have an x plus 5. Now, to find the a in this problem, so I'm now going to have this a times x minus 4 times x minus 1 times x plus 5. So to find a, we have to replace x with 0, and the y is going to be this 16. So what I have then is this a times 0 minus 4, 0 minus 1, 0 plus 5. And that's going to equal this 16. So 0 minus 4 is going to be a -4. So it's going to be a -4, a -1, and a 5. That's going to equal then this 16. So what I have then is -4 times -1 is going to be a +4. and 4 times 5 would be 20. So this turns into 20a equals 16. You now have to divide each side by 16, so a equals 16 over 20. And if you divide the top and bottom by a common divisor, they have the common factor of 4 in them. So that makes that turn into 4/5. So f of x is going to equal this 4/5 times this x minus 4 times x minus 1 times this x plus 5. And I'm going to leave it in that form on this one, but if need be, we may have to expand that out. But sometimes if you put that in to your MyLab math, it may take it, and that'll save us the trouble of expanding it all out. So if I want to find a polynomial function whose zeros are 3, but notice how we have these multiplicities now. I have a multiplicity of 2. I have a -3 with a multiplicity of 2, and it has a degree of 4. So that this really means 2 3s and 2 -3s. And notice that since there's 4 zeros, that means the degree is also 4, so that kind of matches up. And notice how this also passes through a point 2, -75. So we're required to also find the a value here. So if I set this up, I have f of x equals, then I'm going to have this a times, I'm going to have this x, that's going to be actually, since it's a +3, that means that's going to be a -3. So it's going to be a -3 squared times then, and since this other 0 was a -3, that's going to be an x plus 3 squared, since it had a multiplicity of 2. So if I want to find a, I have to substitute 2 and -75 in for x and the y. So I'm going to have then this a times, and I'm going to replace this x with the 2. That's going to be 2 minus 3 squared times then 2 plus 3 squared. And that's got to equal then this -75. So 2 take away 3 is a -1, and -1 squared is going to be a 1. So it's going to be a times 1. And 2 plus 3 is 5, and 5 squared is 25. And that's got to equal then this -75. So what I'm going to have then is 25a equals this -75. And if we divide both sides by 25, a is going to equal then this -3. So my answer here should be then f of x equals this, the a is going to be a -3 times then this x minus 3 squared times this x plus 3 squared. That would be the polynomial function. I would try to put that into MyLab like that first, but if it doesn't take it, we would be required to then expand that all out. So the next thing we get into is graphing a polynomial function using its x-intercepts. So in graphing f of x equals x minus 1 squared times x plus 2, what we can do is first identify the x-intercepts. Okay, we're going to do that. So to find the x-intercepts, remember you have to set y equal to 0. So what this would be then is x minus 1 squared times x plus 2 is equal to 0. So then we would just set each one of these equal to 0. So I'd have this x minus 1 squared equals 0, and this x plus 2 equals 0. So again, notice that if you put a 1 in there, that's going to make that 0. So x would equal 1. But notice how it has a multiplicity of 2. There would actually be 2 1s there. So that has a multiplicity of 2. If I solve for x here, x is going to equal -2. Okay, so I don't really have to put these 2 1s there. I just want to make a little note there that, you know, one of the x-intercept is 1, and I may want to kind of say, hey, there are 2 of them. So a multiplicity of 2. So what's so important about this multiplicity? The multiplicity will describe the behavior at the x-intercepts. If the multiplicity is 1, the graph crosses the x-axis. In other words, the y values will change sign. If the multiplicity is 2 or even, so if the multiplicity is 2 or 4 or 6, the graph is going to touch the x-intercept, but what it's going to do is turn back, and it's either going to look like a minimum or a maximum depending on which way it was coming towards the x-intercept. If the multiplicity is 3, the graph is going to cross, but it's going to kind of flatten out like a snake. So keep that in mind with the multiplicity of 3. That's going to go with 3 or 5 or 7 as well. Another thing we want to do is we want to identify the y-intercept. So we set x equal to 0 and solve for y. So if I look at this problem here, y is going to equal 0 minus 1 squared times 0 plus 2. So that's going to equal a negative 1 squared would be a 1. 0 plus 2 is 2. So my y-intercept is going to be this 2. So the end behavior is going to be used to kind of create the graph. If the degree is even, the end behavior will be the same. Here's the catch though. It's all about that a. If a is positive, in other words, greater than 0, each end will finish in the up position. So we're talking about the far left and to the far right. If a is negative, in other words, a is less than 0, each end will finish in a down position. So in other words, the graph will be opening down. If the degree is odd, the end behavior will be the opposite. In other words, if a is positive, the left end will finish down, the right end will finish up. But if a is negative, the left end will finish up and the right end will finish down. So notice that if we put this all together, our degree, notice how there was actually 3 zeros, 2 1s and a negative 2. In other words, if you notice here, this x occurs twice, and there's this x over here, which means the degree of this function is a degree of 3. So since our degree is a degree 3, we're going to be paying attention to this. The other thing I have to pick up on is what the value of a was. Notice that there is no value of a out here. Notice how the x's are positive. So there's nothing to pull out as far as negativity goes. So the a would be considered a 1, and therefore that's positive, which means the left side should be finishing down and the right side should be finishing up. So if I graph this problem, what we do is we graph the x-intercepts to start with. So we graph the 1 and the negative 2. So the 1 would go here, and the negative 2 would be over here. Another thing we found was we said that the multiplicity is of one of them is a 2. So the 1 has a multiplicity of 2, which means that's going to be a touch. And the multiplicity of a negative 2 was a multiplicity of 1. So they had a multiplicity of 1. So that means it's going to cross. So this is going to be a touch. And this is going to be a cross. It's going to cross the x-axis. So the y-intercept was 2. So the y-intercept was 2. So let's see if we can put this all together. So the end behavior is over here. So what happens is this graph is going to come up through here, and once it gets to negative 2, it's just going to cross the negative 2 since it had a multiplicity of 1. It's got to turn to touch that y-intercept, and then the graph has to approach the negative 1, but since negative 1 has a multiplicity of 1, it's going to touch and turn back around, and that graph should take on that look. So that's how on the far left it finishes down, the far right it finishes up. The x-intercept was a negative 2, it crosses. It has to pass through that y-intercept of negative 2. I'm sorry, y equals 2. And it has to come back down to where that 1 was. But since 1 is a multiplicity of 2, it's going to touch and turn back around and create that graph. Again, if I want to kind of look at this from a graphing calculator perspective, if I want to kind of verify my work. So if I have y equals, if I clear that off, if I put in then this x minus 1 squared times x plus 2, right, graph. Notice how that does kind of mirror my graph. The x-intercepts are -2 and 1. The y-intercept is 2, things like that. So it kind of shows that as well. So keep in mind, the turning points are also called maximus or minimus. So if you notice here, our graph has 2 turning points. This would be considered a maximum, and this would be considered a minimum, a local. The most turning points is always going to be 1 less than the degree of the polynomial. So the degree of the polynomial can be determined by the sum of the multiplicities. So since we had a multiplicity of 2 and a multiplicity of 1, we do see that the degree is 3. Or also you can just multiply the variable. Notice how the variable there was x squared times x, that creates that x to the third as my leading term. So either way you want to look at it, if you know what the multiplicities are, just add the multiplicities together. That will also help you identify the degree. So since the degree is 3, the turning points is going to be 1 less than that. So the turning points at most means there can't be more, there can be less than this, but there can't be no more than this. So if I go 3 minus 1, I get 2. So there can be up to 2 turning points. Notice how this graph does turn once and it turns twice, but it cannot turn again if it's a degree 3 polynomial. So that's why this end behavior, we kind of feel sure about it as well. So if I look at the function f of x equals 4 times the quantity x minus 4 times x plus 3. If I want to find the zeros and their multiplicities, notice how this is already factored for us. So one of the factors is x minus 4. The other factor is this x plus 3. All we have to do is set each one of those factors equal to 0 and solve for x. We get x equals 4 and we get x equals this -3. As far as the multiplicities go, that's where the exponent comes in. So the multiplicities, this one has a degree of 1. So there's only 1 4 present. So there's only 1 4 as a 0. So since 4 is just one of those, that multiplicity is 1. This is going to tell me that the graph is going to be crossing. And at the -3, notice that -3 is going to have a multiplicity of 3. Since this exponent is 3, that's going to tell me that this is going to be more like a snake, or it's going to kind of flatten at the x-intercept. So determine whether the graph crosses or touches each x-intercept. So where the x-intercept is 4, it is going to cross. Where the x-intercept is -3, it's also going to cross. It's just going to look like a snake. It's going to kind of flatten out. Determine the maximum number of turning points. Since the degree was 3, or is it actually 4? Yeah, it's actually 4. So the degree is 4. Notice how we have x here and 3 x's there. That makes 4 x's altogether. Or if you count the multiplicities, 3 plus 1 is 4. The number of turning points is going to be 1 less than that. So the turning points is going to be no more than 3, because 4 minus 1 is going to give me 3. So there can be less than 3 turning points, but there cannot be more than 3 turning points. So as far as the behavior goes, that's where the a value comes in. Notice how a is +4. So we have to use the degree and the a value. Since the degree is even and a is positive, the end behavior has to be the same. And since a is positive, the end behavior the left side should finish up and the right side should finish up. So when I graph this, that kind of guides me along here. So the first thing I do when I graph this is I'm just going to graph the zeros. So we had a 4 and a -3. So I have a 4 and a -3. So what we pick up on is at -3, it's a degree 3, so it's going to cross, but it's going to come like a snake. So, but notice how the end behavior it finishes up. So my graph has to start up here somewhere. It has to come down. It has to kind of flatten out a little bit at this spot here. Kind of makes a snake, so kind of crosses and flattens out there. Okay, so let me just then do a little bit better job of that. That's kind of looks really rough. So see if I can make a snake. Let's see here. Something like that. So it's going to make that little snake, and it's got to turn back around somewhere. Don't know how far down, but it's got to turn back around because it's got this other x-intercept. And since that was a multiplicity of 1, it should just kind of cross over and look something like that. So this graph should take on some look like that. We just don't know how far it goes down. We'd have to find a little bit more information, but we didn't do that here. So let's look at the graphing calculator and see what it gives us here as well. So if I hit y equals and clear this off, 4 times x minus 4 times x plus 3 to the third power, a graph. Notice how it kind of does what we described there, but it goes down much further than I showed there, but notice how it does kind of cross at those two spots. Okay. So it kind of mirrors our graph. And again, we're just trying to get a sketch of it sometimes. If we want more of it, then they'll have to give us more information. So write a polynomial function whose graph is shown. So what we do is, and again, they want to use the smallest degree possible. So notice how this is a touch. That means that has to be a multiplicity of 2. And notice how it crosses there. That's got to be a multiplicity of 1. And notice how it crosses there. That's got to be also a multiplicity of 1. So the first thing we're identifying are those zeros and those multiplicities. So we have a -1 is a 0, and its multiplicity is a 2 because it touches. The other 0 is a 1, and its multiplicity is a 1. And then the other 0 is a 3, and its multiplicity is also 1 since it just crosses. So if I write those as factors, I should have then this, since there's a -1, that's going to be an x plus 1. But since it has a multiplicity of 2, I put a power 2 there. There's a 1, that means there's an x minus 1. And since it's a multiplicity of 1, we keep the exponent as a 1, or we don't show it. And since the third 0 is a 3, that's going to actually be x minus 3 there. So now we want to find is the value of a. So right now we have this f of x equals this a times this here. So to find the value of a, we're going to use that order pair, that 3, 8. So 3 is going to go on for the x, and the 8 is going to go on for y. So what I'm going to have then is this a times this 3 plus 1 squared times 3 minus 1 times 3 minus this here. 3 minus 3. That's kind of confusing me here. Hold on here. Where did I go wrong here? So had some confusion there because my 3 minus 3 was going to give me a 0. And when you multiply by 0, there would not be an 8 in the problem. So I have a mistake there going on. It looks like my zeros were -1, a 1, but that's actually not a 3. That's actually a 1, 2, 3, 4. So y'all caught me on that, did you? So I should have a 4 there, not a 3 in this spot. So let's get that 3 off there. That's not 3. That's not 3. Let's see if that now will work for us. So we should have that third 0 is actually a 4. So it's going to be an x minus 4. So this should actually be 3 minus 4. So if we now do this math, we have a, and then that's going to be 16. That's going to be a 2, and that's going to be a -1 equals 8. So that's going to be 32 times -1 is, so that's going to be a -32a equals 8. So a is actually going to equal this 8 over this -32, which is going to reduce down to -1/4. So if we put this all together, then we should have f of x equals then this -1/4 times this x plus 1 to the power 2 times this x minus 1 times this x minus 4. So if we want to verify that using our graphing calculator, if we hit the y equals button and clear that off, we should have then this -1/4. I'm just going to use parentheses there instead of that other button. So there's my -1/4 times then this x plus 1 squared times this x minus 1 times this x minus 4 hit graph. And yeah, that does mirror the graph that they gave us. So we did a pretty good job there on finding that function because it does match. Okay, so what else do we have here? All right, we have gotten to the end. So hopefully you find that helpful in working with polynomial functions. And we're working with higher degree functions. Again, we're picking up on how the zeros and their multiplicities can help us identify what the graph looks like just by looking at the equation. And also the a value and the degree helps us identify the behavior. Notice how this was a degree 4 and a was negative. It's degree 4 and degree 4 means it should finish in the same direction. And since a was negative, they both finished down. So I'm really liking that answer a lot in that graph. So that concludes our first lesson in Unit 3. Take care.